Welcome everyone to part 4 of my NanoVNA-H4 series. And as I think I've said before, this really focuses on the H4. I love that little instrument. If you have a different kind of or different model VNA, a lot of this information still applies. It's just some of the menu features and stuff aren't the same. In this video though, it applies to every VNA, including commercial VNAs that cost thousands of dollars. I want to talk about wattmeter readings, SWR, return loss, and Smith charts. Now, hold that thought for a minute. If you haven't seen these 3 videos, go down in the comment section below, click on my playlist link, find the playlist DCL-704 test equipment. All my videos on the VNA are in that folder. Okay, let me explain what we're going to do in this video. I know I haven't done a good job yet, but you'll catch on in about 60 seconds. We're going to look at a typical radio system, a transmitter, a feed line, and an antenna. I want to talk about what wattmeters give you. They give you wattmeter readings. You can use those readings to calculate SWR and return loss. Your VNA can also give you SWR and return loss, but it can draw a Smith chart. The reason I'm going to all this trouble in this video is I want you as a radio amateur or a radio technician to get the most out of your VNA and get the most out of the time you spend with your hobby or your work. The more you know of what you're doing, the more fun you're going to have doing it. So that's the spirit in which this is offered. I hope this video is enjoyable to watch, and I intend it to be understandable to beginners and intermediate technicians as well. Let's look at a typical system. What I mean by that, you got a transmitter or a transceiver, a feed line, which is coax, and an antenna. The first thing we usually do, especially in land mobile radio, but even ham radio, we get forward and reflected power readings. So what that means is we put a wattmeter in line. This is a directional bird, but your Heathkit, MFJs, all those, they all operate on the same principle. They're really the same thing. The slug, as you can see, is a 1,000-watt slug with the arrow pointing like it is. If the transmitter is on the left and the antenna is on the right, I'm measuring, of course, forward power. If I spin that slug so the arrow points the other way, I'm measuring reflected power. You do the same thing with this instrument. If you dial the left one up to SWR, key the transmitter, pull the knob out, and set the needle to the extreme right, to the set point, I guess you would call it. Then if you push the knob in without turning the knob, the needle will fall back to a certain amount of reflected power, but it's not labeled a percentage reflected power, it's labeled an SWR. It's the same thing. Now, I'm going to come back to this, so if I've just lost you, don't worry about it. I'm going to tie all this together in a minute. Whatever meter you're going to use as a wattmeter, you've got to put it at the antenna to know what's really going on at the antenna. I'm afraid of heights, so I put my meter here because, again, I'm not climbing a tower to put a wattmeter up there, and I'll just live with whatever reading I get. Later, you're going to learn, and I'm going to show you how, as I said in the last video, how to use a VNA to measure the antenna down here on the ground. Wattmeter can't do that. The VNA can. Anyway, let's move on. So I have forward power going forward. I have some power coming back. I want you to think about this reflected power. It hits the transmitter. Where does it go? If the transmitter presents a perfect non-reactive 50 ohm load, all that power goes in the transmitter and is dissipated as heat in the power amplifier, and if it's high enough, it's going to cause damage. Unless the radio has a fold-back circuit where it detects the reflected power and throttles the transmitter back to keep the heat dissipation within limits. Well, it would be more, and now, here's one other thing. What if the transmitter doesn't present a 50 ohm perfect load? And a lot of them actually don't, believe it or not. Well, then some of that reflected power is going to re-reflect and add to the forward power and head back toward the antenna. So for the purpose of our little demonstration, let's make it a perfect 50 ohms. We can do that literally by putting an isolator in. An isolator is like a roundabout for RF. The rule is when you enter the roundabout, you have to go clockwise and you have to get off at the first exit. So the transmit power goes through it and goes to the antenna. The reflected power comes back, goes around the roundabout, and has to get off at the dummy load. This means the transmitter never folds back, the transmitter never sees reflected power. And if I put a wattmeter right there, it will measure perfectly forward and reflected without any re-reflections out of the transmitter. Let's look at a typical, possibly typical system. 103 watts out of the transmitter, we lose a couple of watts in the isolator, so we have 100 forward and 11.11 reflected. Now there's a reason I picked on that, and we'll get to that in a minute. The VNA cannot measure forward and reflected power, but it can predict what it will be. And you'll see here by the end of the video how it can do that. That is, if I remember to draw everything back together at the end. If I don't, put a comment in the comments below, and I'll have to re-edit my video. I can see myself forgetting that. So we've talked about wattmeter readings. Let's talk about SWR. If I have 100 forward and 11.11 reflected, I could put my meter in here and put it to SWR, set the forward power to the right, push the knob in, and it's going to give me an SWR. The SWR meter is labeled on the SWR scale for what the SWR must be given the percentage of reflected power the needle is showing. SWR meters can't measure SWR because you'd have to measure it over a distance on the cable. The variations in voltage on the cable, it varies all over, and you're going to see that in a minute here. Now this is an old meter I have, and it's really a cool little instrument. Notice on the reflected scale, so I transmit, I set you can't see the knob, I set the knob, set it here, and I flip the button to reflected, the needle falls back to here. That tells me I have a 3-to-1 SWR, but it also tells me I have 25% reflected power. This is what I'm getting at. SWR meters measure reflected power, but they indicate it as an SWR because the percentage of reflected power determines what the standing wave ratio is. So let's talk about what is SWR. What really is it? Well, if I grab this formula and I put 100 watts in here and 11.11 here and 100 here and 11.11 there and do the math, I'll come out with an SWR of 2. So what does this formula tell us? What does it teach us about SWR? Well, excuse me, but I memorized this formula in 1984 so I could pass my FCC exams. This taught me nothing other than how to memorize a formula. It's meaningless. What is SWR? Well, I don't know if you've ever noticed it, but some brochures say VSWR. That's because it's really a voltage standing wave ratio. Now stick with me. This is not nearly as hard as you might think it would be. We've got to look at the voltage on the line. If we use this formula and plug in 100 for power and 50 for the resistance and take the square root, this forward current, this is a current going forward, this is a current coming back. These waves pass each other as they roll down the line, so to speak. And remember, they're sine waves. Well, if we plug those values in, we find out that 100 watts is 70.71 volts on the line. If we plug in 11.11 watts, we find out that's 23.5 volts on the line. Now think about something. These two waves, this one's going this way. This one, well, they're currents. This one's going this way. This one's going that way. Sorry. In places, these two sine waves are going to add. They're going to be in phase. When they add, what's 70 plus 23? Well, it's 93, plus you add the fraction, it's 94.2796 volts. That's pretty easy. What about as they pass each other, when this one is out of phase with this one? Now they're going to subtract from each other. They're going to be 47 volts. So you see, if I have no SWR, I have 70 volts on the line. If I have SWR, suddenly, I don't know what I have. This is what it looks like on the line. Now, we've got peaks at 94 and valleys at 47. Well, what if we normalize the 47 to a 1? That means we have to divide the top by the same amount. These fractions are equal. That's a rule of mathematics. That means if the 94 is a 2, the 47 is a 1. We now have an SWR, a standing wave ratio of 2 to 1. Why is it standing? That's the funny part. It's standing because even though the two currents are passing each other in opposite directions, where they line up in and out of phase is stationary. The length between the valleys and the peaks are determined by the frequency. The higher frequency you go, the closer together these peaks and valleys are. I will talk more about that math in a later video. Remember, if I had a 1-to-1 SWR, it means the peaks and the valleys are the same thing. There are no peaks and valleys because I don't have any reflected power. If I've got a 2-to-1 SWR, look what happens. Now you know why they tell you don't run too much power if your SWR is high, because your coax can't handle 1,000 watts at a 2-to-1 SWR, but it might handle it at a 1-to-1 SWR. And of course, I'm making the numbers up. I don't know what your coax is rated for, but you get the idea. The higher the SWR, the less power that coax is going to be able to take before it's going to flash over. If you're curious, and I did do these to scale, okay? These cartoons I know look silly. They are to scale. A 1.5 to 1 would look about like that. I think I got the scale almost right. And believe me, I spent over an hour on those graphs that you're looking at right now, just to make them scale properly. So we learned about SWR. What's return loss? Return loss is in some ways the simplest thing in the world. With return loss, we can predict what the forward and reflected power levels are going to be within reason. We can't take into account the transmitters folding back, but other than that, we can predict. Let's say I have 100 forward and 11.11 reflected. Well, that math is a little inconvenient. Let's pretend I had 10 watts reflected. Let's look at a chart of dB ratios, because return loss is measured in dB. If I have one of something, say 100 watts, and what comes back to me is 1/10 of that, say 10 watts, my return loss is a negative 10 dB. We would just say 10 dB because it's a loss. We know it's negative, it's a loss. Well, the question is, if it's 11.11 watts, what is the dB in return loss? Well, 11.11 is slightly more than this, so it's going to be slightly less than 10 dB. I'm going to predict 9.5 dB return loss. Doesn't it? I'm sure that sounds reasonable, right? Well, how could we measure this? We know that 11.11 watts reflected is a 2-to-1 SWR. If I were to make a 2-to-1 SWR, my VNA will tell me what the return loss would be. How can I create a 2-to-1 SWR? Well, actually, it's real easy. Here's another formula for you. If you have, say, a transmission line and an antenna, and they're both perfectly resistive, purely resistive, no inductive reactance, no capacitive reactance, then this formula works. So if I have a 50 ohm load and a 50 ohm line, I have an SWR of 1. We already knew that, didn't we? If I have a 100 ohm load and a 50 ohm line, I have a 2-to-1 SWR. If I have a 50 ohm line and a 25 ohm load, I have a 2-to-1 SWR. So I need a dummy load of 100 ohms or 25 ohms. I don't have either one. But what I do have is two 50 ohm loads I can put in parallel, which gives me 25 ohms. Now I can make a 2-to-1 SWR. So let's hook that to the VNA and see what it thinks. All right. Now, first of all, in the little white box, I have a 50 ohm line with a 25 ohm load, so I know my SWR has to be 2. So I look up above, and I find out, well, it's not a perfect 25 ohm load. It's got a tiny little bit of reactance, and it's a little less than 25 ohms. So my SWR is a little off, but not bad. Okay, you got to admit, it's not bad. Now, we already know that if this was a transmitter, I could put my wattmeter readings in the formula and come out with an SWR of 2. So this checks out. I mean, that's fine. But what's my return loss? Well, I said 9.5 dB. Well, first of all, I'm pretty good with the numbers, and second of all, I already calculated it before I made the video, and you already knew that, didn't you? So 11.11 watts, as I said before, or 11.11% of 100 watts is slightly less than a negative 10. So the minus 9.48 makes a lot of sense. Now, what we've learned about the wattmeter, the SWR, and return loss is a 25 ohm load on a 50 ohm line gives us a 2-to-1 SWR, 11.11% reflected power, and a minus 9.48 dB return loss. The point is, all of these mean the same thing. They all can be measured and calculated with a wattmeter, but they're just expressed on different scales on different terms. So we're done with that. Now, I left the Smith chart out, didn't I? I'm going to gloss over this quickly because the Smith chart is a story unto itself. I'll deal with that in a later video. What I wanted to show you, I'm sweeping my 40 meter antenna, as you can tell. Let's take everything off but the Smith chart. I'll go through this quickly because we're going to go over it much more later. It's showing a 52.5 ohm load with a tiny amount of capacitive reactance. That's why the little cursor is just to the right of that intersection. You see the intersection of the two lines, that's 50 ohms. So it's just to the right saying I'm a little more than 50 ohms. You can't see it, but the cursor is just slightly below the line, not really much. Okay. Now, I'll do this quick. If I went down to 5 megahertz, you'll notice that the resistance has dropped and inductive reactance has gone through the roof. My point is, though, we know that we were here and we've gone around this loop. So slightly below frequency of 40 meters, my resistance is almost the same. It's just almost the same. But it's become very capacitive reactive. Well, that makes sense because if you're if your whip is too low, is too short, the frequency of the antenna is higher, and the antenna becomes capacitive. That's why you put a coil in the bottom to cancel out the capacitive reactance. Now, what I'll get into in a later video is why this curve does what it does, and I'm going to talk about how accurate this measurement is. I'm on about 60 feet of cable here, and yet my measurement at resonance is accurate. And as I go lower in frequency, it stays accurate. As I go higher in frequency, it seems to stay accurate. All right, let's sum up. First of all, those numbers. If you didn't already know, the 52.51, I did a typo here. I meant to say 52.51. That's the resistive value. This is the reactive. A negative reactance is capacitive. A positive is inductive. But when you see the little m, that means milli. So that's a capacitive reactance of 0.0165 ohms. In other words, if you see the milli, it's almost completely insignificant. Don't even worry about it. As I said before, the indications you get for accuracy of a Smith chart will show you what your load presents at the coax connector, but only when you are connected to the antenna through a very, very short cable. The only problem is that statement's not completely true. There are ways of accurately measuring what your antenna looks like when you're not right close to it. I'm going to leave you with that teaser until next time, and I will explain to you how you can measure the antenna a long way down the coax cable. And I'll comment on how accurate it is. Is it perfectly accurate? Well, it can be. Most of the time, it's reasonably accurate. We'll talk about that next time. I'm surprised I got through this in 22 minutes. If you only knew how many times I muted the mic and stopped this so I could cough. I can't believe Texas is this hard to live in. I don't mean to keep talking about myself and complaining, but I love Texas, but I don't like allergies. Okay. In a future video, I'm not sure if it'll be the next one or not, I want to take a good look at the Smith chart. I want to show you how easy it really is to understand and use. I want you to understand how helpful it can be. And I want to stress, you don't need an engineering degree to understand the Smith chart. You absolutely don't. I also want to show you how the Smith chart can calculate the SWR. Remember I said if the load is not, and the line are not purely resistive, that little formula doesn't work, like the 100 ohms over 50. Well, guess what? If the load is reactive, and you know what the reactance is, and the resistance, the Smith chart can tell you what the SWR is going to be. Anyway, the other thing I want to talk about, and again, this will be a separate video, is to go back to that thing about how you can evaluate your antenna, even though there's a long piece of coax between you and your VNA and your antenna. And like I said, I'll leave you with that teaser until next time. I don't normally do that to people, but I'm kind of having fun telling you that yes, you can measure an antenna on the end of a long piece of coax. I hope this was interesting. At least we got in it 24 minutes. That's not too bad. Thank you so much for watching. Please, it is July 11th. Please give me at least a week or more to get the next video up. Thanks so much for watching.